All right, so we're doing section 4.2 today. I don't know if you looked at 4.1. This is going to be a little bit different than that. And we're going to be talking today about this word here, permutations. So this is going to be in contrast to something that I'll teach you later, which is a combination. Permutation is something just to pay attention to. So permutation is basically the number of ways we can order objects when you can tell the difference between them. So for instance, the letters A and B has two permutations. So I can write it as AB or BA. Those two are very distinct, so I can switch them and it makes a difference. So let's take a look at this. So if I've got 4 students, I've only got 2 here today. If we've got 4 students who want to line up to go outside, we want to look at how many ways can I arrange them. So there's 4 spots that I have for going outside. So this is your who's going to line up first, who's going to line up second, third, and fourth. So I've got 4 different positions in a line. If I look at how many options do I have for people to be in first? So I've got 4 students, yeah. So any one of those 4 students could be first. But then if I look at the second, 1 student's already taken up. Whoever's in first, they're in first. They cannot be second. So then there's going to be 3 options, yeah. And then 2 options, and then there's 1 option for the end. Perfect. So these are the number of options for each. And as I showed in 4.1, there's something called the fundamental counting principle. If this is the number of ways for each option, if I want the total number of ways, I just times these all together. It's 4 times 3, 12, 24, right? I have my set of notes here, just so I don't mess up. Yeah, so 24 ways. So with only 4 students, we can have 24 different ways that we arrange those students. So this one is a permutation because students are distinguishable. I can tell the difference between student 1, student 2, student 3, student 4. So let's try a different example. This, you can tell how dated this set of notes is because we can talk about iPods, which are like non-existent at this point. So if you are putting your songs on shuffle and you've got 6 songs, we want to know the number of playlists that we can make with just those 6 songs. So I can look at the exact same kind of pattern. I can look at first, second, third, fourth, fifth, sixth. How many options would I have for the first? I've got 6. 1 of those songs is taken up, so 5, yep, and then 4, 3. Good, so you're starting to notice the pattern, right? So multiply these all together. So I could have 720 playlists. That's only 6 songs. You can imagine now with, if you've got 100 songs, it gets pretty big. Let's try another one. I've got 5 different books, textbooks, math, chemistry, physics, English, biology. How many ways could I arrange those? Same method. So I've got 1, 2, 3, 4, 5 textbooks. So I've got 5 spaces. Same pattern. 5 times 4 times 3 times 2 times 1. Kids, each time I'm using up one of those textbooks, and I end up with 1 less. So this one is 120. So you can recognize the pattern, right? However many number of items I have, so here I had 5 books. I started at 5 times 1 less each time. Here I had 6 songs, so I started with the number 6 times by 1 less, 1 less, 1 less, 1 less. Same thing here. I had 4 students, so I started at 4 times by all the ones below that. So this is so common But we've actually got a special term for this. This is what's known as factorial notation. Factorial notation. So what this is, you might have seen this on the calculator and wondered what it is. This is your exclamation point. So basically what that means is, whatever number is here, I take that number and times by everything until I get 1. So take the number, minus 1, times it by that, minus 1 times by that, minus 1, and so on. So for 1 factorial, this one is just defined as 1. 2 factorial, 2 times 1, so that's 2. 3 factorial, 3 times 2 times 1, so I'll give you 6, and so on. So 4 times 3 times 2 times 1, whoops, or 5, and then 6. We just did that one up above. 6 times 5 times 4 times 3 times 2. So then each of these have numerical values. 24, 120, and 720. So I'll give you a sec to finish writing that down. Any questions on this? Or does that make sense? Okay. So this makes it really easy. Because if I say I've got 50 different items, instead of having to go 50 times 49 times 48 times 47 and so on and so forth, you just put it in your calculator as 50 factorial. And it calculates it for you. Have you seen the factorial notation on the calculator before? It depends on the calculator, but it should be there. On mine, it's above the x to the power of -1 up at the top right. Do you see an exclamation point? Yep, exactly. So if you wanted to do this, you can try it. Go 50, and then the exclamation point, and see if you get a number. You just do shift and then that button. So you should get like 3.04. Yep, perfect. Good. So I mean, you could try that out with the different ones. You can try it with 1, 2, 3, 4, 5, 6. See if you get these, but it should work. So that's essentially what you use for these types of questions. If it says you have this many items, and the key thing is you cannot repeat the items. So for the textbooks, I can't have the math book and then another math book and then another math book because you only have one of them. Exactly. Good. So we're going to use this kind of a pattern to see how this works now if I put a variable in there. So the thing with factorials is these numbers always need to be whole numbers. So 1, 2, 3, 4, so on and so forth. And they cannot be negative. If you put a negative in there, it won't work. So if I now tell you this, n factorial, we can expand this out like we did here. So if we look at the pattern for this, let's look at 6. So if I did 6 factorial, I first started with that first number. What was there? So in this case, I've got n. Then how did I get the number 5 from this? Yeah, so I took 6 and I minused 1. That gave me 5. So I'm going to do the same thing here. N times n minus 1. So I did 1 less than 1 before that. How did I get the number 4 here? Yeah, so I took the 1 before it, subtracted 1. So if I take this one, I take n minus 1. If I subtract another 1, it gives me n minus 2. N minus 3, n minus 4, so on and so forth. Yeah, so we don't know how many numbers there are. So what we're going to do is we're going to put the 3 dots saying this keeps going until we get 3 times 2 times 1. Eventually, I need to stop at 1. So if in this case, suppose I tell you n equals 6. So if we did this, I'd get 6 times 6 minus 1, which is 5, times 6 minus 2, which is 4, and then it would be 3, 2, 1. So this works. If this was 50, it'd be 50 times 50 minus 1, which is 49, 50 minus 2, 48, then it would keep going until you eventually reach 1. So that's essentially what this is. Now let's try these two other ones. This is where typically it gets a little bit more tricky. So what if I had n plus 1 factorial? What would be the first term?
1.
No, it wouldn't be 1. So just like here, if n is here, this term is n. If here I have n plus 1, my first term is n plus 1. And how would I get the next number? It's not going to be plus, because remember I'm always subtracting 1. So it'll be n plus 1 minus 1, which would just be n. And then we're just continuing on with what we see up here. So 1 less than n minus 1, n minus 2, n minus 3, and this is going to continue till we reach 3 times 2 times 1.
Well, the n minus 1 is the same thing as without the log.
Yeah, so I'm going to start at n minus 1, then go n minus 2, n minus 3, and I'm going to keep getting smaller. And where students typically mess up with this is they start adding 1 instead of subtracting 1. So this is n minus 1, then get smaller, n minus 2, get smaller, n minus 3, times, keep going, till 3 times 2 times 1. So this is going to be important as we try and solve some of these problems. We'll get to in the next page. Any questions with this? Okay. Just give you a sec till you write it down. So now let's try some numbers with this to figure this out. One thing to note with this, 0 factorial is defined to be 1. So just as a notation for that, if you ever get 0 factorial, it's just 1. So let's try the following. Try typing 10 factorial in your calculator, see what you get. Just to make sure it works for you.
3, 6, 2, 8, 8.
Perfect, yep. So yeah, 3, 6, 2, 8, 8, 0, 0. And then give the next one a try and see if you can get that one too. As I try and do it too. You might have to put the times sign between the two numbers at the bottom. Okay, perfect. So that's pretty easy. If you're given numbers, not too bad. You can just put those into the calculator for the most part. I'm going to show you a case where it doesn't work. So now we want to look at simplifying some with variables. So if you're given something like this, and you're asked to simplify this, let's just look at what the definition of this is. So we've got n plus 3 all times this factorial. So I've started with n plus 3, and let's just expand this part here. So expand this second bracket. So that'll give us n plus 2 times n plus 1, because we're getting smaller, times n, and keep going until we reach 3 times 2 times 1. And so with this, this is the exact definition of n plus 3 factorial. I start with n plus 3, minus 1, I get this one, minus another one, minus another one. So this is fully simplified. So this you cannot type in the calculator. This is just a variable. So the same way you cannot put something like this. You can't put that in the calculator because you're not solving for it. It's just an equation. So how about something like this? There's a very specific strategy that we're going to use in this case. So in this one, we don't know how long this goes for. It goes on for a long time. But what I'm going to do is look at these, and which one of these, the top or the bottom, which number is bigger? Is n plus 1 bigger or is n minus 1 bigger? Yeah, plus 1 is bigger. So what I'm going to do is I'm going to take the bigger one, so this one's bigger, and this one I'm going to expand. Yeah, so I'm going to expand this one until I reach this one. So I'm going to go, okay, on the top, I start with n plus 1, then minus 1 just gives me n, and then I reach n minus 1. That's the same as the bottom. So we'll leave that factorialized. Factorialized? I think that's the right term. And the reason I now leave it like this, we've got n minus 1 factorial on the top, n minus 1 factorial on the bottom. These cancel. Now I have no more factorial, and I'm just left with n plus 1 times n. And that's simplified. You don't need to, don't bother multiplying that out, just leave it like this. Does that make sense? So this is a strategy that you're going to use. You're going to look at which one's bigger, top or the bottom, and then expand until you reach that bottom number. So let's try this strategy now with this question. So here I've got n plus 2 on the top and n on the bottom. Good. Expand the top. We got n plus 2 times n plus 1 times n. I've reached what's on the bottom, so I leave it. And those cancel. And again, don't multiply these out, just leave it as n plus 2 times n plus 1. So that's going to be your strategy for this. Let's try one more. So I've got n minus 3 factorial divided by n. Which one's bigger? The one on the bottom. Good. So we're going to expand the bottom. So we'll leave this up top, n minus 3 factorial over n times n minus 1 times n minus 2 times n minus 3. I'm the same as the top, so leave it. And then those cancel. And this one's the tricky one, because if I'm expanding the bottom, these numbers need to stay in the denominator. So I need to leave it as 1 over n times n minus 1 times n minus, oops, not 3, n minus 2. So these need to stay in the denominator. I see this very often where you cancel that out, and these magically go on the top. So just make sure you leave them as fraction. Any questions with that? Okay. So with these ones are really easy. You can just plug them into your calculator. The one that I want to focus on is a number like this. So if we did 1052 factorial over 1050 factorial. So try plugging that one in your calculator and see what it gives you. I think those numbers are big enough. Perfect. Okay, good. So it gives you an error, right, with this? So the reason why your calculator gives it an error is it tries to calculate the top, which is a big number. It's like 1052 times 1051 times 1050 times 1049 and so on all the way down to 1. It's a huge number. And then it tries to do the same on the bottom. So this won't work in your calculator. These ones, plug in your calculator, you're fine. This one won't work. So what we're going to do is we're going to use the strategy we did up here. So instead of n, we've actually got a number. But the same thing we're going to do. So just look at these. Which one's bigger? The one on the top's bigger. So expand this out until I reach the bottom one. Now I've got it. Got it like this. Cross out the sames. Now it's really easy. Just 1052 times, yep, just times this. This one I don't have in my notes. So 1052 times 1051, 110562. So 1,105,652. So this strategy is also going to work on numbers as well. Because on the test, I will give you something like this, where I give you a number that won't work to put into the calculator, so you'll need to know that strategy. Make sense? Okay. Do I have some more examples? Yeah. Do I want to do this? No. I'm going to say cross this page out. Don't worry about these questions. If you can do the others, that's as much as I want. So just cross off this last page. So that's 4.2.